Welcome to the Switchbox Speaker Series. I'm your host, Jack Maddens. Switchbox is a think tank that provides legislators and advocates with rigorous and actionable data analysis on state climate policy. The Speaker Series is an opportunity for our community to learn about and discuss the latest policy and technologies driving state level climate action. The first half is on the record and recorded, and the second half is for off the record discussion. Today, the City of Ithaca has a bold mandate to electrify their entire building stock. Where do they start? Which buildings will yield the most emission reductions most equitably? Typically, energy engineers create a digital twin of an individual building to simulate the results of various retrofits. But figuring out which buildings to retrofit first would require a digital twin of an entire city. Researchers at Cornell, together with RMI, have done just that for the city of Ithaca. Here to talk about it today is Timur Dogan, is the director of the Environmental Systems Lab at Cornell that created that digital twin model for the city of Ithaca. And Hung Ming is a researcher in that lab. They'll break down what's new about their approach and what other cities can learn. Welcome, Timur, Hung Ming.
Thank you so much, Jack. Thank you everyone for joining. We are really excited to kind of share some of this work with you. I'm calling in from Germany, that's why it's completely dark. And Hong Ming is also kind of on the go. But we are really excited to be here and to kind of share some of the work. I'm going to share my screen and kind of jump right into the presentation. And first of all, I want to thank some of our supporters here and collaborators. First of all, at RMI, we've worked really closely together with Steve Abbott and Jingyi Tang. They have been really amazing at kind of making this possible, as well as the kind of grid innovation team at Avangrid, who are kind of behind all of the validation data, energy usage data that we had, as well as funding from Cornell Atkinson that make this possible. And last but not least, of course, Rebecca Evans from the City of Ithaca, who has been kind of really great at kind of facilitating this work, bringing some of the findings into the policy making and kind of day-to-day operations of the city. So how can digital twins enable session of our talk? And we want to dive right in and kind of show you how we built this and how you could leverage this. So let me take a step back though first and talk about how this all came about and what the motivation behind all of this is. On the left, you see kind of the typical pie chart around like building operation and carbon emissions accounting for almost 30%, and that's globally. In the city of Ithaca, actually, the carbon emissions from building operations are just a little bit higher. And of course, then the city passed this really kind of ambitious so-called Green New Deal to be carbon neutral by 2030. And we, as Cornell University and the lab called the Environmental Systems Lab, we were really interested in how can we help the city reach this goal through some of the research that we have been doing and focusing kind of more on single buildings, as Jack mentioned already, our lab specializes in kind of simulation of single buildings and helps architects and designers to create more sustainable buildings for new designs. But of course, the existing building stock is a significant problem that needs to be kind of looked at. And carbon mitigation really in the existing building stock will be incredibly important to kind of reach these carbon neutrality goals and not necessarily new construction. And so we looked at this kind of with this multi-objective kind of goal in mind, looking at transportation, the shift from gas-powered vehicles to EVs and the charging infrastructure. How can we help design that? We looked at kind of ways of motivating more active mobility solutions, shifting trips away from personal cars or vehicles. And then, of course, the other question is around energy supply, looking at geothermal and solar, as well as storage capacity, long-term and short-term. And then lastly, of course, we are interested in looking at the buildings, looking at their envelopes, how do they have to be upgraded, and then can we combine the retrofitting that needs to happen with some of the other kind of pressures on the city, such as creating affordable housing and can we maybe find synergies between those things? So those are the ambitions, and we are, I think, still work in progress. Not everything we will not touch everything in this talk, but just to kind of give you a sense that this is kind of a broader, multi-objective kind of task ahead. So in this presentation, we want to talk about how we created the digital twin, how we leveraged it, and how you may want to leverage technology like this. And then we'll share some next steps just to get you excited about some of the other things that we're working on at the moment. And so let's dive right in with a really complicated diagram that shows kind of how we created the digital twin. And I'll unpack it kind of step by step. So on the left-hand side, you see kind of this GIS data, which is publicly available data that is mostly available throughout the US. So we're using building footprint data. We're using height information about buildings, and we can leverage what we call LiDAR, or what's so-called LiDAR data, which are basically 3D point clouds describing the built environment that are basically the city has been scanned from an airplane that flew over the city and kind of created this point cloud of the city. And then we use that to extract building geometry from these data sets, and it has to be extracted in a specific way so that kind of our engineering models and analytical models can understand it. That's what you see at the very top. Then, of course, this building geometry needs to be paired with information about like how this building what is it made out of? And so we are pairing this with a construction archetype library that we apply here, and we're leveraging some of the other data points or metadata that we know about these buildings, such as when has it been built, what construction classification does it fall into, what kind of siding material is it using, and these are kind of properties that are typical of a tax assessment, and so we're using that plus the geometry to kind of assign construction. And then, of course, it's also really important to understand what's going on inside of the building, how is it used, and what are the energy usage patterns inside of buildings, and that has to do with how are buildings occupied, and how are people using, let's say, electric appliances in buildings. And here we are again leveraging text information, but also we are leveraging the so-called DOE reference buildings for some of the time series assumptions that go into this model. And so we bring this all together, and then we have a model for a single building. And then we automate this process for the entire city. So we have a unique model for every building in the city and pass this on to what we call the simulation engine. And so we use kind of open source validated tools like Energy Plus and Radiance for energy simulation and radiation simulations as well, ray tracing simulations. And we have also developed a more custom kind of energy modeling toolkit that is significantly faster so that we can run these simulations at an adequate speed, which is a low order model, or a so-called 5R1C model that is also kind of widely validated, has been an ISO standard for a very long time, and so very trustworthy kind of physics simulations that we're leveraging in this digital twin. These models, of course, all require a few other inputs, such as weather data. Here we use a combination depending on what the purpose is. We use historic weather data that's been recorded in the local airport, but we also use typical meteorological year data, which is a statistical kind of averaging of a longer period of time to kind of even out the odd moments in climates in a year that can happen, like extreme events and so forth, to get a better kind of general sense what the energy consumption would be in the city. But on top of that, sometimes you also may want to actually look at the extreme weather cases to look at, for example, resiliency scenarios when it's like a heat wave event that happens once in a while. And so that there are other kind of ways you can compile this weather data, and that give you kind of interesting insights in that sense as well. And that being a simulation tool, of course, it's really exciting that then you can try all kinds of things in these models. So once you have what we call a baseline model, that describes the status quo. We can then try out different scenarios. We can group buildings together differently to understand like what are potentials here for geothermal systems, for renewable energy potential in the building and so forth. And so this first step, once you have kind of assembled the digital twin from all these geospatial data sources that we're tapping into, the first thing is, of course, to look at how accurate is this. And here, of course, the utility data is paramount to be able to do this. And we had access to building data for the entire city of Ithaca, and now we're scaling this to all of Tompkins County. We have now gotten access to that. And you see the first graph shows you a histogram that compares the energy usage in the model, which was our first guess, and in the metered energy usage, metered billing data from the city, from the utility. And you see these kind of distributions don't match perfectly, but they're also not that far off. If you're considering like the assumptions that we have to make, all the data gaps that exist in kind of describing existing buildings in a city, it's quite phenomenal to see that these kind of physics models can actually make a really good first guess. Of course, there's uncertainty in some of the parameters that we assume. We, for example, do not have information about how leaky is a building from a air leakage perspective, or how poorly insulated is a building. We do not have an exact U value for each and every building. And so you can then use the utility data, of course, to fine tune your model. That's what we call a calibration step, when we basically pass this on to an optimization algorithm that iterates and tries to find solutions that really match exactly the built energy usage data, with fine-tuning some of the parameters where we do not have an exact number, but we can define a plausible range. And then you can get really, really close in terms of accuracy with the baseline model. And so that is then the basis for any of the subsequent steps where we talk about scenario simulations, and Hung Ming will talk a little bit more about that in the next step. On top of these kind of building energy models, we also have kind of a rooftop solar model built out. It's a slightly different simulation approach where geometric fidelity really matters. So here we are leveraging the LiDAR data from the city, taking into account vegetation, precise roof geometry, and so forth. And you can see in this map, you can then show where exactly should you put your panel. This is, I think, a 50 by 50 centimeter resolution that we are kind of giving the city on the rooftop for solar potential. And so let's move on to how to leverage the digital twin. And I'm going to pass this on to Hung Ming, who will take it from here. Thank you.
Yeah, thank you, Timur, for the introduction. So after we have a calibrated urban building energy model, our first question is, how do we explore the building retrofit solution space? So given an unique building, we divided up into 10 categories in terms of the building systems. And this is according to the NREL's energy efficiency measures database. So that database has the approximate cost, for example, replacing your furnace into an air source heat pump, or the cost of upgrading your envelope to code. And after that, we want to explore like what's the best combination for the homeowners to pick. So we selected a maximizing metrics that basically divides the kg CO2 reduced by the upfront cost plus operational cost. And we select this over a 15-year air source heat pump lifetime. So next. So after we have the best solution that has the highest impact of benefit cost ratio, our colleagues can simulate the data on a web viewer, and then we can display the different scenarios. For example, on the top left, we can see the baseline scenario, the envelope to code, the air source heat pump plus hot water upgrades, and the fourth one is envelope to code plus hot water, and the final one is if we also combine PV and envelope plus air source heat pump. So we can now understand the monthly end use of the heating and the cooling load as well as the lighting and the hot water loads. And in this web viewer, which we will show later, we can also use the different metrics such as EUI and also EUI per capita, and also the carbon emissions reduction rate for each building. Next. And the next question the mayor and the director of sustainability has is like, we have 6,000 buildings, but how do we define the priority for each building? So we sort of invented this diagram that has y-axis as benefit cost ratio. So the kg CO2 reduced divided by cost, and the x-axis is the sorted buildings. And next. So after this, we apply the color code. The blue one is single family residential, the green one is multifamily, and the red one is commercial. So if you look at this graph from left to right, you can sort of understand which building groups should we start first. So in this simulation, the commercial buildings has a higher benefit cost ratio, and then it's the single family residential, and then it's the multifamily group, and finally, the commercial buildings that are hard to decarbonize. Next. But after we run the first simulation, we wanted to understand what's the effect of the city's incentive structures. And this includes incentives at the state level and also at the federal level. So we simulated the effect of weatherization assistance program, the residential tax credit 25C, 25D, and the commercial 179D. And what's surprising for us in these two graphs is that originally the city thought they should start with commercial buildings. And this is the result of the top graph, which is no incentives. But actually, when we run our simulations that also includes incentives, we found out that the multifamily residential has a lot more potential because a lot of these multifamily buildings can get incentives to potentially cover the entire upfront cost. And this is what the city didn't know before. And if you look at the bottom graph, the sorting order changes because of these incentive structures. And now the sorting groups are we do multifamily residential that has a lower income first, and then commercial. And then the third group is a mix of residential plus single family plus multifamily buildings. And then in the middle group, we have a chunk of single family buildings. And then we get to some multifamily buildings. And then in the end, there are commercial buildings. Next. So after we have the grouping, we were interested in creating like a representative archetype building that tries to analyze the cumulative cost for 15 years. And this allows us to see the payback period and also return on investment of these retrofit upgrades. And on the left side, you can see the multifamily residential prototype. And on the right side is the single family prototype. And we mapped out the 4 scenarios, which includes the baseline, the air source heat pump only, the air source heat pump plus envelope, and finally the air source heat pump plus envelope plus rooftop solar. And we can see there's a 8 to 10 year payback period, which is an investment gap that could influence homeowners' decision to say if they want to retrofit their buildings or not. Next. So our next question is, where exactly are these buildings? So on the left is the grouping in terms of the mapping of the city of Ithaca. And after we have this mapping, we can do district heating plans according to like grouping similar heat loads of the buildings together. Or we can think about how do we decarbonize a neighborhood of buildings together to reach like a synergy between these similar heating and cooling loads. And on the right side, we can also set the timelines for decarbonization and allows the cities to set goals in terms of from 2030 to 2050. Next. So last week, we presented this research at the National Institute of Building Science in Washington, D.C. And it was a really interesting experience because we got to interact with stakeholders such as the U.S. Department of Homeland Security. And we had a conversation with Dr. Garfield Jones, and we were thinking about how do we scale this up to the county, to the state, or even to the national level. Next. And our publications include research articles on RMI's website and also the SimBuild 2024 conference in Denver. And we included the QR codes here. So if you're interested in, you can scan it. And our newest updated abstract was accepted at the Building Simulation 2025 conference. So we hope to see everyone in Brisbane, Australia next year. And next, Timur will explain the next steps for the Environmental Systems Lab.
Thank you so much, Hung Ming, to walk us through this. Yes, so let's talk a little bit about the next steps. So we are kind of working on making this data useful for multiple stakeholders, of course, not just the homeowners. This is kind of a lens of that same viewer that Hung Ming showed that is trying to kind of make this digital twin data useful for the utilities. And it's kind of showing an electricity grid mapped out here with all the feeder lines, and it will render kind of the peak load in the winter and the peak load in the summer, as well as the load duration curve, kind of showing the hourly load data on these networks. And you can select a specific intersection in the network to see kind of what the load is like there, and you can kind of aggregate and kind of look at everything together. And this is, of course, quite critical once we are kind of starting about talking about electrification of the thermal loads in buildings, and then potentially later also EVs. We are really facing, I think, capacity limits in the network, and we can kind of quickly show where is the load reaching nameplate capacity of the feeder lines with this kind of tool, and kind of helping the utility understand where they have to do investments and how they can steer maybe some of the retrofitting in a certain direction, where they want to maybe install some battery buffer storage to kind of make sure that these loads don't peak too high. And at the same time, we know some of the kind of data that we are using for the digital twin that describes the buildings is somewhat limited. We would, of course, love to have much better models to describe the building stock to create even more accurate models down the road. And so we've partnered with Bentley Systems here, who have generously kind of supported some research that we've been doing with a group of undergraduate students, Amber, Curtis, Ann, and Tony, who have been really amazing at kind of taking these textured mesh models that you can get from photogrammetry, but also now Google has opened its photorealistic tiles data sets, which makes this then available kind of in all the major cities in the US and some of the major cities globally, which is fantastic when we are thinking about scaling this approach. And basically what we're doing is we're using image segmentation on these kind of textured models to understand what are we seeing, such as windows. We could kind of detect photovoltaic systems already installed on the roof, and maybe even start sizing some of the HVAC systems that you could see kind of sitting as a box on top of the roof as well. As I mentioned, we are really interested in kind of seeing the bigger picture with the digital twins, these urban digital twins, and seeing the bigger picture also means like integrating it with other systems. And so in a parallel research track, we have been working on a tool called urbano.io, which is a fully fledged mobility simulator, which can reproduce kind of cell phone-like, cell phone movement patterns using simulations. And this has been validated in Los Angeles and New York City against cell phone data, but also against kind of mobility counts that happen in the street with kind of demonstrated really good accuracy here. And so the goal for us is to kind of add to this digital twin in the next steps a mobility layer that also connects with the energy consumption modeling to understand this link between the buildings, the energy use in buildings, as well as EVs, but also understand kind of for the city, what's the decarbonization potential of if it manages kind of to motivate more walkable environments and create a mode shift, leveraging more public transit and so forth. So that's a really exciting kind of project moving in parallel, but we'll connect shortly. We're also interested in, of course, what happens kind of within buildings. We've in the past kind of developed a tool called Eddy3D, which is a microclimate simulation tool that produces highly resolved microclimate simulations in between the buildings in the streets, trying to understand what's the thermal comfort in public spaces and streets. And of course, that's critical when we're talking about heat wave mitigation and resiliency planning. Another one of those layers that would be fantastic to have inside of the digital twin. And so Hung Ming has also worked really closely with KPMG and a Norwegian company called Augment City, where this idea of combining energy modeling, mobility modeling, and kind of other resiliency components such as flooding, which was kind of modeled by KPMG and Augment City, kind of overlaying all of that in the Augment City digital twinning platform, kind of bringing it all together, making it accessible to all the stakeholders that can use this kind of 3D visualization platform. And now, of course, we besides these kind of research improvements, we're really interested in expanding the impact of this kind of digital twin model. And so we've created this really, really short onboarding survey. If you're interested in participating, if you're working for a municipality or a community that is interested in actually building one of these digital twins for your community or municipality, please feel free to just kind of go in here and add the information that we're asking about. Leave a contact. We'll be in touch for a quick Zoom follow-up call to discuss potential steps forward. And we've thus far had really great responses, and we're excited to kind of build like a community of cities that want to use digital twins for their decarbonization efforts. And so, yeah, you're welcome to join, and we're really excited. Thank you so much again for listening and joining in. It was a great pleasure to be invited here, Jack. Thank you so much. And again, thanks to all the collaborators and the supporters of this project.
Excellent. Thank you so much. Ithaca is swimming in data at this point, and we have a number of questions in the chat that are highly technical that I want to get to in a moment. But one thing I'm curious about is, obviously, this has created a ton of data to inform the City of Ithaca's decarbonization strategy. What have you found is the single most useful thing that you've provided them, and how are they using it today to decarbonize their building stock? Is it that sequencing and targeting of the particular building subtypes, or is this a input that's mostly being used by Ithaca's utilities to prioritize some of their grid investments?
Yeah, fantastic question. Thanks, Jack. And Hung Ming chime in right after. In my mind, this technology is a conversation starter. That's the biggest contribution of this kind of data and data visualization. And so a conversation starter, what does that mean? It means many things, of course. So first of all, this prioritization. I think that was a fantastic conversation that we had. And I think it's one of the biggest kind of contributions, I think, of the work that mostly Hung Ming did with the cost modeling, is understanding where are the low-hanging fruits and how can we chase them. Because these buildings are the no-brainer conversions to make. And the city, to get the ball rolling, needs to engage with these homeowners and really kind of convince them that they should be doing this. They should use this data that we provided to kind of targeted outreach and get kind of the community excited about this, but also mentioning some of these incentives to them, because I'm pretty sure most of these homeowners do not know how many incentives they would qualify for and how kind of how impactful these incentives could be for their property. The second thing that I think will need to happen with the help of a digital twin is to kind of bring and the policy side bring in a retrofitting building code to kind of set the standards. Like when do you need to retrofit, to what standard, to what level, what's achievable, what might actually create too much of a burden for homeowners, and how can we help. How can this kind of be used to right size certain things? That's the second kind of component. And then yes, the utility, of course, is very interested in understanding the impact on their grid. And it's quite interesting to see. I mean, that they do not really have these kind of detailed modeling capabilities of buildings and the loads happening. And for forecasting, that's really, really helpful. The other thing that we are hoping to do, and we haven't really done that yet, is to actually open this data set up to the community. So I think a lot of these kind of decarbonization efforts need buy-in from the community. And so the hope is that with the data, one can have an informed discussion, and one can convince maybe the more skeptical homeowners, and maybe one can convince kind of funding agencies and so forth to steer support in the right direction to make this an equitable conversion. The other thing is we're trying to automate tedious tasks for maybe even some of the contractors. So we're at the moment looking at heat pump sizing and finding like the right projects for contractors, because we also have worker shortages, right? But if we wanted to do all these retrofits by 2030, we'd have to import a huge workforce into Ithaca to really make that happen. And so there are some interesting ideas there. And similarly, if it's about like district networks and so forth, we just recently had a conversation with a district heating network installer who was really excited about the fact that we have a way for him to identify potentially nationally where would a district network really make a lot of sense. And so this is for them like I don't know, maybe like a marketplace to identify the economic opportunities for that company.
Hung Ming, did you have anything you want to add there?
Yeah, thanks, Timur. Those are really great points. And one thing to add is that the city of Ithaca currently is like trying to go beyond just data energy simulations. They're trying to like assess the quality of life of the improvements of these retrofits. For example, they're looking at not only energy, they're looking at resilience of these flood events. So we're trying to like communicate these complex models in very simple language. And this doesn't mean it's easy. It's actually pretty hard to like explain these variables or these simulation to the general public. And we wanted to like try to really bring this out, and like we're currently working on an engagement impact fund. So like how do we bring these models outside of the academia environment and really engage with the homeowners, the city officials, or even just like the tenants in Ithaca. Yeah.
I could almost imagine, since you have all the parcel information, automating letters to the homes and the building owners that have the highest potential for cost benefit as a result of each decarbonizing dollar. I want to get into some of the more technical questions that have been raised in the chat, and I'm going to start by handing the mic to Switchbox's own Director of Data Science, Max. Are you on, Max?
Sorry, yeah, is that better?
Yep, that's better.
Yeah. Great, sorry. I'll just say, first off, fantastic presentation, a lot to digest here, a lot of really amazing stuff. So you actually already answered my first question, which was on the grid GIS side of it. Seems like eventually, like the first slides didn't show that, but that you got that in later on, which is fantastic. And so the question that I guess I'm being called on then by Jack is the next one, which is, so it sounded like you built your own energy simulation modeling. And so I'm curious what led you to do that as opposed to using Ochre or some of the other like sort of next generation modeling tools that are out there. Like, was just like a timing sequencing thing? Are there certain things you wanted to do that weren't possible to do in tools like that?
Yeah, so we started with Energy Plus, which is widely used, right, for building energy simulations, and it's a fantastic tool for single building applications. And you get a lot out of this software in terms of detail and engineering precision. But applying it at scale is really, really tough, and it's computationally intensive, it's data intensive, and so we kind of took a step back and said, okay, like to do this kind of calibration that we want, we need something that can allows us to iterate really fast. And so we built a low order model. It's not something that we invented necessarily. It's again, it's an ISO standard kind of approach to simplified building energy modeling that we implemented. There was just no kind of implementation off the shelf that one could use. And so we kind of implemented a 5R1C model, which has some shortcomings when it comes to simulating kind of hourly temperature, for example, temperature levels indoors and so forth. And also in some of the more cooling dominated climates, you might see like some inaccuracies, but nothing in the order of magnitude that would be worrisome for kind of an urban application like the one that we have in mind. With you take into account the uncertainty of all of the inputs that we are dealing with. And so I think it's a great tool. This simulation that we showed basically runs like in under 2 minutes on my old MacBook here, and it's 5,000 buildings in under 2 minutes. And I think that's the right kind of computational intensity for these kind of large scale simulation approaches. We know of this kind of ORNL, which is one of the national labs, did this great presentation once about creating an energy model for every building in the US, and they were kind of using supercomputers for these kinds of analyses. And I think that's not right. That's there's something about accessibility and of these tools. We really want to bring this to small town communities that do not have like a subscription to a supercomputer. So the idea is really to kind of make this accessible for everyone.
Yeah,
That's great. I had one more question. Oh, sorry, go ahead.
Oh yeah. You can go ahead.
I had one more question I'd love to pass off to somebody else, which was, are there other technologies like the district heating or thermal storage or other things that you're excited about that might make a big difference of the kinds of things that interventions that would be, plausible in the space? Thanks.
Yes, very excited about this. I think we really have to look at this. Like if we simply electrify buildings with air source heat pumps, one building at a time, I think we are missing out on a huge potential. And so this is, I think, why this geospatial modeling is really required to understand kind of where are there clusters of kind of maybe similar loads or opposite loads that would really be suitable for these kind of district systems that you can implement at much larger scale with higher efficiency. And then, of course, energy storage is a big question, short-term, long-term storage. And so Ithaca has invested in like hydrogen for long-term energy storage, and then battery for the short-term storage. And I think just understanding like the order of magnitude of a system that you'd have to have, like we can do that with this energy model, and then you can decide, like, make trade-offs. Do you want to invest in a larger storage capacities, or do you want to maybe take the money and put it in the building retrofits to lower the load so that you can downsize some of these systems? I think all of those things we haven't really like talked about in detail yet. I think that's going to come in the next couple of months, I think, with the city.
Yeah, and the city of Ithaca is currently trying to do bulk purchasing of air source heat pumps. So we're trying to like categorize what are the prominent heat loads for them to see what are the discounts that they can get. For example, like 1,000, 2,000 heat pumps at a time. And so, yeah, I think those are really valid points.
I mean, that's huge, and certainly something that would be great at even a state level. If we want to
Yes.
have ambitious decarbonization across the whole state, can we do bulk purchasing to bring price down? Would be amazing.
Yeah.
Max, I just want to do a quick tee up. Is there a books for broilers plug that you want to do here, and how might, if this model existed for the entire state of New York, how it might change the estimate or forecast we have for that legislation?
So just to give some context on what Jack is saying, one of the projects that Switchbox has worked on, we have a couple projects trying to estimate the kind of the missing money gap, like how much would have to be provided to households in order to make the payback periods something that is palatable for individuals, in places where there is in fact energy savings, like investing upfront to unlock long-term energy savings through electrification. And so, yeah, I mean, right now we are looking at buildings independently, not imagining kind of the like thermal network side of things. I think there is a lot of, I mean, this is a much greater level of detail than I think, and our models are even one step removed. We're just trying to figure out, like how large do the subsidies have to be to make these things make sense, as opposed to saying like, do this building, then that building, then that one. But I do think that, if we had this level of detail, it could really inform, statewide policy right now is pretty broad brush, and being able to say, these are the towns or these are the cities that are going to benefit the most, both in terms of people's pocketbooks and in terms of the total carbon emission side, I think would be enormous. And I can imagine, using that to build coalitions, with local groups. I mean, obviously Ithaca, people are already very, inspired to make a difference for the environment, for sort of altruistic reasons. But there are plenty of places across the state where just like, like who could have the most savings unlocked by doing this kind of work and doing it in a way that is also good for the environment at the same time would be enormous. And so I think that's stuff for us to think about in the long run, for sure.
That sounds very exciting, and I would love to talk more about this and how we can help.
Excellent. One quick question. I'm going to continue us on one policy thing, which is 2 weeks ago we talked about a whole neighborhood decarbonization program in California that's basically allowing for utilities to cover the costs of electrification when it's cheaper than replacing the gas pipeline in that neighborhood. And I was wondering if you guys have thought about including that in your cost benefit analysis, or how difficult would it be to do that?
It's fantastic that you bring this up. I mean, we've talked about exactly that with the utility partners, and I think for them it's sometimes difficult to it's a big company, and the data that one would need for this is managed in different places, and so they said this is interesting, but I think they need some time to get information about expected lifetime of some of the network pieces, and then it's the sense that I was getting from the group that we are working with, which is the Grid Innovation Group, is that this is complicated for them, and it will take them some time to kind of wrap their head around this. But at the same time, I know that they are doing this because I live on a small street in Ithaca where they are offering exactly that, to shut down the gas pipeline or the gas line. They are offering to cover the cost of electrifying the buildings. And it is, I think, a very smart approach that you do not invest in legacy infrastructure anymore, and you try to kind of use the money differently and channel it in different ways, because, I mean, it's just a very sensible thing to do, right?
Yep. I want to pass it to Kartike. We have about 10 more minutes left. And so he's asked a question about tax assessment data. And please introduce yourself. Oh, you're on mute.
Yeah, hello. So I'm a PhD student at Concordia University, where we're trying to build similar urban energy platforms for City of Montreal. So the question that I had was that how did you, understand the tax assessment data well enough to extract useful information out of it? Because the experience that we have faced is City often does not, harmonize the data that it has collected. So for example, above ground floors, below ground floors, it was very difficult to convert that information into something that an energy plus model can use. So how did you, what was your experience inferring that data?
Yeah, and I mean that data might vary in quality. So I think in our case, the tax assessment data was quite detailed. I mean, I didn't grow up in the US, so sometimes it's always surprising what level of data is publicly available. In this case, the buildings were described with a lot of detail, and things like what heating system it's using seem to make a big difference in how kind of taxes are assessed, and what construction system does it use that has like some insurance policy implications, how much combustible material is there. So these kinds of pieces of information are not directly what we need, of course, but they allow you to make some really good inferences, which helps you to kind of create models that are getting closer to the truth. But of course, none of this is perfect, and there's for sure some miscategorized and mislabeled buildings in our model. In the big picture, it doesn't seem to matter. And of course, when we say, well, now we've found you like 100 buildings that you should target, maybe a couple out of these 100 will actually be will not be kind of correctly placed in the group. But I think to find that out, you really have to go to the buildings, and or you have to start collecting data differently. So just to kind of add this here as a plug as well. I mean, so for example, in Ithaca, it was quite difficult to get utility data. We worked for over 3 years to get the utility excited about this and to share utility data. But
Wow.
within, for example, New York City, the policies to kind of report energy usage make this public record for larger buildings, for commercial buildings, right? So I think taking what we have built for Ithaca, we could redo that in New York City without kind of having to even negotiate with a utility company, which doesn't like to share some of the data, maybe for privacy reasons. Maybe they don't want to share it for other reasons as well. But I think that their policy in a city can make a huge difference. Like, how are we collecting data about our building stock? Are we collecting the right data to support the energy transition? And so once the city kind of includes some of the energy usage reporting in their policy, you will have access to this data, or at least the city will have access to this data, and will be able to kind of maybe share this much more easily with you than a utility can. So I think that's kind of maybe something that's quite useful to kind of know if you're talking to policymakers, how can they rethink how they collect data.
Okay.
Excellent point. I want to bring in Meltem to ask a question about your use of LiDAR point cloud data.
Oh, hi. Thank you. I am Meltem. I'm a graduate student from Carnegie Mellon University. So my question is basically, what's the process you use for coming up with the clean roof 3D models from the footprint and the LiDAR point cloud to run solar simulation afterward?
Oh, very, very detailed question. Well, so we tried a couple of things, and we tried work that came out of TU Delft called Polyfit. I'm not sure if you're aware of that, and we worked together with Liang Yang, who was the PI on this at TU Delft. He's a professor at TU Delft, and this workflow was amazing in some cases, but couldn't handle, I think, some of the poor resolution of our data. And a lot of the buildings are kind of under thick tree cover and so forth. So this didn't kind of work perfectly. And so we ended up for the rooftop reconstruction use kind of like other kinds of models where we relaxed a little bit, like to say the precision requirements and like requirements for like simplified low polygon count models like in Energy Plus. That's one of the other big benefits of kind of using your own engine. You can just kind of say, well, we actually don't care if the building has 500 triangles that define it versus like just like a small subsection of that. So if you've ever used Energy Plus, you know what I'm talking about. The more polygons, the slower the simulation, and so we kind of went kind of a middle path where we used I think you could probably describe it as simple mesh draping over the point cloud. And key to this was good classification of the point clouds so that you know what's a building roof return and what's vegetation. And then once you have that and plus the footprints, you can create like really good mesh drapes that you can then use to calculate roof areas and orientation of surfaces. And because we're using kind of a quasi non-geometric energy model with the 5R1C, all we care about is the area of something and its orientation, and we can kind of circumvent all of these problems that you would encounter if you used Energy Plus. But you're bringing up a really good point, and I think these, digitally reconstructing cities in a way that these models can be used in analytical simulation software is a big, I think, research topic that still requires some work.
Thank you.
Excellent. I'm going to try and get one more in here. Iyuan, you have a question about interactions, modeling interactions between buildings.
Can you hear me okay?
Yeah.
Yeah.
Please introduce yourself too, if you have a chance.
Yeah, I'm a senior engineer at Big Data Software. And just a quick question about the interactions between buildings in the sense of like maybe a long wave radiation between the envelopes and some heat energy flow networks between buildings, like for resilience purposes. And I guess that's another common practice right now. Like you can essentially trade energy between residential buildings if you have EVs and solar panels in the future. And want to hear what your considerations there.
Thank you. This is a great question, Ewan. No such thing as long wave radiation. We didn't model that. We did invest quite a lot in kind of shading calculations, making sure that we also include the vegetation correctly in the overshadowing calculations. This is something like I know from the best practice in urban energy modeling. Vegetation is often really difficult to include, and therefore often it's not included. So this is a step forward, but no long wave radiation interaction between the buildings. We are thinking that this is also not going to affect the energy consumption predictions too much. But the other considerations that you bring forth, this kind of district energy systems that you could leverage here, we have not implemented kind of a model that simulates them, but we can basically provide the necessary input data that would go into a model like that. Through kind of providing at each building node, we can provide you with hourly heating and cooling load data, and then you can simulate these kinds of networks. And I think there's a huge potential there, and that's probably one of the next steps that one has to look into, is kind of like how to maybe even include some kind of simple form of district energy sharing or energy distribution network in these kind of models. We've already kind of talked with, as I mentioned, the company that does these kind of installs these kind of systems, and I think there was huge interest in kind of like getting that in their hands to kind of use that as a way to find opportunities, find the locations where it would be very feasible to implement such a system.
Yeah, and one last thing to add is we're trying to like quantify how much additional peak load it would be increased if we electrify all buildings in the city of Ithaca. And like how would that affect the grid itself? And can the infrastructure handle that? And so, yeah, it's just a small point to add between the interactions between the buildings and the grid itself.
And I'll add one more thing on some Switchbox work. We've been thinking about this as well, and how different rate designs might impact when those peaks actually hit.
Yes.
And so if this is something that you guys are thinking about, also chat about that as well.
I'm going to go into bonus time for just one question, which is, you had mentioned that we need policymakers to demand the publication of this data by utilities and other entities. And so I wanted to give you the soapbox just for 1 minute. If you could talk to every policymaker in the country, what is the data that needs to be made available in order for these models to be run that does not exist today in abundance? Or I should say, if not exists, is not accessible.
Yeah, I think energy usage data, if it's not precise, but just some kind of like classification, like energy use in this range, A, B, C, D, kind of like a school grade that means something that would really help to kind of validate the models and even validate some of the assumptions about buildings. The other thing that could be really helpful is permitting data, because then you understand what has changed in the building stock over time. And the third thing would be maybe a more structured way of storing information about buildings. And I know that's a tall order. Could you imagine something like what BIM did for the construction industry? Could you imagine something like City BIM to kind of manage data in a structured way, also manage the geometry and the metadata together, so that you never really lose sight of it. But the first two, I think, are the important things that would really make our lives much, much easier.
Now we know what is on your data Christmas list. And with that, I'm
Yes.
going to close us out. I'm going to give a plug because in 2 weeks, when we return, or I think maybe 3 weeks, when we return, we're going to hear how Minnesota has been doing integrated resource planning, and part of that has been requiring utilities to submit some of this data to their PUC. So if you guys are interested in a more policy-oriented conversation, please join that one. And as always, thanks for joining the speaker series. I want to thank our speakers for the excellent presentation. We really look forward to seeing this scale out and grow.